webinar. Okay.
Okay.
Good afternoon for the participants in Japan, and good morning for the participants in Europe. As it's currently midnight in the United States, it's unlikely that we have no participants from US. Thank you for joining I²CNER seminar series. I am Masanobu Kubota, professor at I²CNER. I am going to be the chair for the webinar today. It brings me great pleasure to see so many of you in the virtual audience. Once again, a warm welcome to the I²CNER webinar. I²CNER launched this seminar series in 2010. Since then, we have had the privilege of hosting numerous distinguished researchers from around the world. Our speaker today is Professor Cynthia Volkert from the In-situ of Materials Physics at the University of Göttingen in Germany. First, is there Professor Ishihara today? いらっしゃる。Firstly, we will hear a few words from the director of I²CNER, Professor Tatsumi Ishihara. Professor Ishihara, please.
Okay. Thank you very much, Kubota Sensei. My name is Tatsumi Ishihara, the director of I²CNER. So first of all, thank you very much, Professor Volkert and Cynthia. Today's very interesting webinar, and we are very looking forward to your interesting and exciting result. And as you know, the I²CNER has very strong activity on the hydrogen brittlement because of the Masanobu is strongly progressed of the these activities, and we are very looking forward to have your interesting result and some of the collaboration result we are expecting. So today, thank you very much to accept and talk of your result in this webinar series. Thank you very much.
Thank you very much, Ishihara-sensei. So before we begin, I'd like to take a moment to remind you that we will have discussion after the presentation. During presentation, please keep your microphone muted. This webinar will be recorded by I²CNER. However, recording by the audience and taking screenshots and photos of the presentation are prohibited. All right, next, I'd like to introduce Professor Cynthia Volkert. She is a new PI of the Advanced Energy Materials Trust in I²CNER and joined us in this April. So fresh PI. Right? Currently, Professor Volkert and I jointly have an international research project on creep in hydrogen, supported by both JSPS in Japan and DFG in Germany. We have observed a significant acceleration of creep deformation in the presence of hydrogen, which poses a potential challenge for the safety of the advanced high-temperature hydrogen technologies such as SOEC and SOFC. To elucidate the mechanism by which hydrogen accelerates creep deformation, I expect Professor Volkert to make a significant contribution because she is a renowned researcher of the dynamic behavior of nanoscale materials and in-situ electron microscopy. Actually, she possesses a highly advanced TEM equipped with an environmental cell, including temperature control and an actuator for mechanical testing within the TEM. Professor Volkert obtained a bachelor degree in physics from McGill University and a PhD from Harvard University. She spent 10 years at Bell Laboratories focusing on iron-solid interactions shin metal film deformation, and electromigration. Later, she moved to Germany, first to the Max Planck Institute for Metals Research in Stuttgart, and then to the Karlsruhe Institute of Technology, before settling in Göttingen in 2007. In 2008, she served as the president of the Materials Research Society and has been a member of various advisory committees and boards, including those for the Humboldt, Max Planck, Leibniz, and Helmholtz societies. Some of her current research interests are understanding the remarkable mechanical behavior of wood, unraveling the mysteries of new creation, detecting order and avalanche processes in metallic glasses, and studying the material degrees of freedom that control energy dissipation at sliding contact. So, all right, let's move on to her presentation. Her talk today is about in-situ TEM study of the effect of hydrogen on crack propagation in steel. So, Professor Volkert, please begin your presentation.
Hey, thank you very much. I hope you can hear me well. If not, you'll say something, I think. So yes, it's a great pleasure and honor to have the opportunity to present some of our results on in-situ microscopy studies. I'm going to talk today about the in-situ TEM studies of crack propagation in steel and the effect of hydrogen. The talk will focus a lot on the methods we use, trying to understand and tell you what the TEM is good for. That's also because that will help to explain how we hope to play an important role in the study that Professor Kubota just discussed about the hydrogen creep, effect of hydrogen on high temperature creep in metals. So I'll spend some time talking about what the TEM can do, and then I'll show you our results and tell you what we've learned from those results. This work has been performed, the TEM work has been performed by the excellent hands and eyes of Dr. Lin Tian, and she's here on the call. She's the second Professor Cynthia Volkert here listed in the participant list. So she will, if there are questions directly to her, she will be able to answer them. And it's performed in collaboration with Professors Kubota, Sofronis, and Kerkheim, all well-known experts in the area of hydrogen embrittlement. So we've had very, very solid support in understanding our in-situ TEM studies and how we can interpret those in terms of hydrogen embrittlement. So that's the plan for today. And I'll just give a couple of view graphs reminding you all, although I believe you all know it better than I do, about hydrogen embrittlement. The talk I'll present today, the results I'll present today are on a low alloy tempered martensitic steel, so it's in the ferritic state. And so the results I'll show are also from this material or ones that are very similar. So the problem with hydrogen embrittlement is exactly that it does what its name says. It's very detrimental to mechanical properties, and you see that here for the case of stress-strain behavior, where when there's hydrogen present, failure sets in earlier. And what you see it in a very marked decrease here in the fracture toughness of the material. And so that's the reason, the technological reason why this is so important. It's as simple as that. And of course, one wants to understand why hydrogen has this effect, and one does things like looks at the fracture surfaces. And here you see images of fracture surfaces for samples that have been fractured in nitrogen or in hydrogen. And you can see that there are quite distinct surfaces, that they're quite different. I'll show a higher magnification in a moment, but generally at this large magnification, you can see this scale bar here is 500 microns, which is 1/2 of a millimeter. So this is quite a large scale, and you can see that the hydrogen surfaces are flatter, and there's less features on the surface, fewer features on the surface. And if we go in and look more carefully, one finds really very distinct behavior or features on the surfaces. At first glance, maybe if you're not used to looking at these, you think, well, I don't see big differences, but in fact, there really are important differences. If you take a look here at the case that's fractured in nitrogen gas, and if it were fractured also in argon or vacuum, it would look similar. We have features that we call dimples. There are small sort of openings, and basically we'll conclude, and as has been concluded throughout in the literature, these kinds of dimpled surfaces result from voids forming and coalescing at the crack front, and that what you see here is basically half of the side of a void, the surface of a void that have coalesced to form this fracture surface. So that's what we see here. You will also see these occasional, these around features like this one I'm pointing at right here. That is a precipitate, a carbide precipitate, and those are found on the surface of these fracture surfaces. Now, if we look at the hydrogen case, it actually looks quite different. Here you see there are almost no dimples. You might argue there's some dimples over here, but to a large extent, it's dimple-free, and what we have are sort of small facets or small steps that are fairly flat. We also have some larger regions that are quite flat, and because macroscopically this looks flatter, also as you saw in the previous micrograph, one talks about these surfaces as being quasi-cleavage surfaces. They're called cleavage because that's typically referring to a split along a crystal plane, but it's called quasi because if one looks in, it's not a crystallographic plane that's happening here. That's the surface here, although some of these features do have crystallographic orientations. Some of the small facets do tend to have particular orientations, such as 100 facets, depending upon the material. So that's what one sees from the outside. And then when one tries to understand what are actually the mechanisms that lie behind it, what one ends up concluding is that the embrittlement is controlled by the defects in the material and the fact that hydrogen interacts strongly with those defects. So that's the basic idea, and I think everybody agrees at that point. But after that point, which defect interactions with hydrogen are relevant and controlling, there's a lot of discussion, a lot of different opinions, and probably that's because for every material and under different conditions, there's probably different combinations of mechanisms that are controlling. So it's surely not one single mechanism for all materials, or even for a given material under a given set of conditions. Even there, it's very likely that a number of mechanisms will be contributing to the role of hydrogen in the failure of a material. And so it's certainly a complex process. I've tried to show you, excuse me, some of the mechanisms here using this very nice schematic from the Max Planck for iron research. And if we look over here on the right side, this is the microscopic or the atomic length scale. And here what the red dots are supposed to indicate hydrogen. And what they're trying to show here is that the hydrogen does in fact interact with all kinds of defects, interfaces, dislocations, and vacancies. And then we see the microstructural scale here further to the left, showing segregation of the hydrogen again. And then here all the way on the right, where there's a crack, hydrogen-induced crack at the surface of the material, they show you schematically some of the mechanisms that have been discussed involving interactions of the hydrogen with various features of the microstructure. For the case of the low alloy steels that I'll be talking about today, and for the room temperature conditions that we'll be talking about, the two mechanisms that are mostly discussed for gas, for the case of embrittlement in gas, are the so-called HELP mechanism, which stands for hydrogen enhanced local plasticity, and the Heyde or hydrogen enhanced decohesion. I believe I may not have that quite right, but this one, and the two ideas are the following. For the help mechanism, the idea is that the hydrogen enhances the local motion of dislocations. Where there's high stresses and where there is hydrogen, dislocations move more easily. The reason for that enhanced mobility is argued to be either a reduction in the shielding between the dislocations, which interact with each other through their long-range stress fields, or through hydrogen that is segregated to the core, which allows nucleation of kinks and the motion of those dislocations easier. So those are the two ideas for the help mechanism. And the Heyde mechanism is one where one argues that the segregation of hydrogen to interfaces lowers their energy and makes simple cleavage along particular crystallographic planes easier. So that's the idea, the two mechanisms that are discussed the most here. And we'll see if we can say anything about those two mechanisms during this talk. So it's clear that one wants to gain control of this hydrogen embrittlement problem, but as I've just said, it involves defect dynamics that are at the atomic scale. So if one wants to really understand which mechanisms are active to find ways to mitigate the problem, one needs to get measurements and methods that give you atomic scale resolution and sufficient temporal resolution. That's already a challenge. In addition, hydrogen is the hardest element to detect because of its lightness. And let's add to that the fact that crack propagation is typically very often an unstable process. So if we want to look at what's happening at a crack tip, we have to find a way to control the propagation of the cracks. So these are the challenges one has if one wants to look at this problem at the atomic scale, and with some time at the dynamics, we need some kind of temporal resolution. And I think it's clear that a single experimental or theoretical method will not be able to do all of this, and a variety of methods must be used. And the one that we want to offer and are able to offer here is the in-situ transition electron microscopy. The promise of that is that it does give almost atomic scale imaging of dynamic processes. Real-time resolution is easy in the microscope, and if one has a lot of funding for expensive cameras, one can also go to even shorter temporal resolution, sort of faster resolution in the time regime. So what I'm going to talk a bit about today is the methods we have developed to introduce hydrogen into a specimen inside the TEM. And I'll also talk about our methods, and this is something that has taken us around more than half a dozen years to develop methods for controlled crack initiation and growth of a specimen inside the TEM so that we can watch what's happening at the crack front. So that's what I'll start with, is talking about those things. But before I do, the TEM is a powerful tool, and you'll see what it's good for when I show you the results. But there are, of course, some challenges to the TEM results, and I want to start with those and be upfront about those challenges. And so let me list them here. The first one is simply the fact that the electron beam does produce damage in a material. So here you see a schematic of the inside, or the electron path inside of a TEM. There's a source for the electrons, and they move down the column through a series of electron optics. And here's our sample, and basically this is where the transmission electron microscope gets its name, is that the electrons are transmitted through that specimen, and it's on the far side of that specimen that we use various imaging modes or diffraction modes to learn things about the material through the interaction of the electrons with the atoms and electrons in the specimen. That means that the specimen needs to be very thin. It also means that the electrons are interacting with that specimen, otherwise we don't get signals. And you can see a variety of the things that happen as a result of interaction with the electrons with the specimen. There's a lot that happens. And particularly on this, what we mostly are looking for in the TEM is the transmitted electrons, which can be either elastic or inelastically transmitted. They give different signals that we can use in different ways. But you also notice there are other electrons generated. Those will be important on the next few graphs. So I just wanted to mention them, particularly the secondary electrons that you see listed here. These, there are many of those. For every primary electron going through the specimen, there are at least several secondary electrons generated. So there are quite a few of them. They have quite a bit lower energy, but they are not always able to be ignored. So in this process of this primary beam transmitting through the specimen, there's a whole lot of things, as you can see, that go on. The ones that are important for us, or the ones we're most concerned about, the problems, the changes in the material that are most significant are listed down here below. We create local heating. So the excitations generated primarily in the electrons of the material are then relaxed to thermalized, and we end up with local heating in the material. We can break bonds in the material through the interaction of the primary or other electrons with electrons in the material. We can end up with what's known as radiolysis and break bonds, which of course changes the material. We can even in some cases end up with direct knock-on of atoms in the material, and that we actually are able to knock atoms out of their lattice sites or their positions in the specimen. So these are things that an electron beam can do. They typically produce damage that is characteristic, and from our experience, we're able to we know what damage looks like. And I'm going to just say here, we saw no evidence or no obvious evidence of the effect of electron beam damage on our observations. So to first order, we're going to say it's not significant here. But I do want to say this is, I believe to first order this is correct, but it is something that it's an assumption here at the moment that's based on our experience. We have materials, and you'll see one a little bit later, namely wood, where the damage from the electron microscope is very significant, and we see that right away and must find methods to avoid it. But for the study, the steel, there appears not to be significant differences, significant effects of electron beam damage. So that's an important challenge for the TEM that always needs to be considered. And in this particular case, we believe that it's not the main effect of what we're observing here in our materials. Another thing that is always a question, particularly well, for the case when one tries to introduce hydrogen into these microscopes. There are these so-called environmental microscopes, which is what we have, which allows us to put a low pressure up to around 10 millibar of hydrogen into the chamber. And the studies you'll see today are performed at 2 millibar. And for all of those who work with hydrogen embrittlement, and they're going to say, well, that's not enough to get anything to happen. Room temperature and 2 millibar of hydrogen is not going to cause anything in ferritic steel. Despite that, in many different materials, or in a number of different materials, various studies across the world for groups that have these environmental TEMs have found that despite these low pressures and despite room temperature, one sees hydrogen effects on the material. So the conclusion is that in some way or another, the electron beam inside the microscope is significantly increasing the fugacity of the hydrogen, so that we're producing enough hydrogen in a state that it can get introduced into the ferrite in this case, or into the other materials and other studies, that in fact we do have significant hydrogen in the material. Now, there are known cross sections for electron-induced gas phase dissociation. And if one just simply uses those values, we would predict an increase in the amount of dissolved hydrogen over what one would expect for 2 millibars at room temperature by a factor of 100. Might be enough to make some difference. However, we know from studies at the University of Göttingen that the hydrogen atoms and ions that are created by the electron beam are captured almost immediately on the TEM chamber surfaces. And the result is that the concentration of hydrogen ions in the gas state is 10 to the 5 times lower than predicted based upon those known cross sections. So this idea that we're simply producing a plasma of hydrogen atoms or ions in the chamber with the electron beam, and that this raises the effective partial pressure, dissociation is no longer necessary on the surface, and as a result, one argues you increase the amount of dissolved hydrogen. There seems to be some problems with this argument. We think things that need to be considered are the fact that we charge these specimens because of the secondary electrons that get admitted. They become charged, the specimens. There very often is a layer of absorbed water on the surface. We haven't considered yet the possibility of the electron impact causing dissociation of adsorbed hydrogen that's already on the surface of the specimen. Those things have all not been considered. So we may have electron beam induced dissociation at the surface, maybe changing that and making it easier. We may have electrochemical effects simply due to the water layer there and the potential of the specimen. So we have a lot of questions that are unclear about how the hydrogen gets into the specimen in the TEM, but everyone finds very clear effects of the hydrogen, so we know it's in there. We do not know how much is in there. That's something that is absolutely, we have really no idea. We can only say, yes, we clearly see an effect, or we do not. And in our case, we did clearly see an effect. One thing that we can say is that in ferrite, for the time scales we're dealing with and the length scales we're dealing with in these lamella, the hydrogen will have had time to diffuse and equilibrate on the time scale of our specimen. So whatever concentration of hydrogen we have in the specimen, it's been able to find its preferred sites within the material. And so it's free to move and find it and equilibrate there. So these are huge issues one has to think about. In our case, the result is we don't know what the concentration of hydrogen in our specimen is, but whatever it is, we believe it to be equilibrated. Okay, so that's the further challenge. And now the challenge that I brought up at the beginning, which is how do we actually control crack propagation in a specimen in the TEM? And here I'm using this sketch from the Max Planck again for a specimen that's being pulled on under tension. And it's easy to see that one would expect that this stress concentration that results at the head of this crack tip is going to lead to propagation of this crack. And if we think about a bulk specimen, then out of the plane of the view graph, the material extends infinitely or quite a long ways. And so the stress state here is what's known as plane strain, and the so-called triaxiality is high, which means that plasticity is low. If this is a thin film like a TEM lamella, then plasticity becomes much, much higher. We're in a situation of plane stress. And the nature of the stresses, this triaxiality, are all the stresses in all three directions equal, is what triaxiality is a measure of, is very important because it controls the amount of plasticity that can go on. And this is completely different in a TEM lamella than in a bulk specimen. And this is a difference that we cannot ignore. Our observations are made on specimens that are in a completely different stress state than the bulk specimens. Plus, there are very easily accessible surfaces, which are not so accessible in the bulk specimens. And these are surfaces that have often seen various processing, such as focused ion beam machining. So there are really significant differences in the stress states. I should point out that the plastic zone size in the materials I'm talking about today is much larger than the thickness of the lamella we're dealing with. So yet another length scale at which another aspect of this process where there's strong effects from the lamella that we have. So the conclusion here is these are very different. This is a significant difference, and drawing any interpretations from our results to the bulk state, which is where we want to understand what's going on, we need to really do that with care. And so the talk that I'll present today, I'll present our results from the TEM lamella, and then I'll tell you to what extent and how I think that tells us something about the bulk state. So that's the plan. But let me now just tell you how we actually perform those experiments in the TEM. So if I have the specimen I just described here, where I basically put it under tension and then the crack will progress, as the length of the crack A increases, the stress at the crack tip also goes up. It goes as the square root of this crack length. So if I were to look at the stress intensity factor, as it's called, at the crack tip, K1C, for this case, it goes up as the crack extends. Now, there may also be there's a resistance of a material to crack propagation that depends upon changes in the defects, many different processes that can occur in the material, and they're summarized together in something that's called the crack resistance, or the R curve. It may go up, it may go down for material, it depends what it is. But the point is here is that if this K1C gets larger than the resistance of the material to propagation of the crack, then the crack becomes unstable. And so if I have a geometry where I'm loading the specimen, as I show here, where I have a crack and I'm pulling on it in tension, it's almost certain that it's going to become unstable. And if you think about a thin sheet of say, aluminum foil that people use in the kitchen, if you pull on that, you know that it will rip, that once you start a crack, it will fail very easily. And that's a statement of what I'm showing here, is that as soon as you have a tear in that material, that crack then propagates very easily, even though aluminum is typically a very ductile material. And if you were to think of working with it, at the bulk level and not of a thin film, for instance, you might expect that there would be ductile deformation and not sort of propagation of a failure crack. So that's the problem with putting a specimen into the TEM and just pulling on it and trying to look at the crack tip. It will inevitably become unstable and move much too fast to investigate it. So we made a different design, which is a modification of the so-called double cantilever beam geometry. And you can see the geometry here. We cut out 2 posts of material with a thin lamella in between. This thickness will be around 150 nanometers. We're going to look through that with the electron beam. We cut a notch in this material, and then we come in with a wedge-shaped tip, and we pry these 2 cantilevers apart, causing then, let's see, I think I can get this to, excuse me. Causing then this notch to form a crack, initiate a crack, and to propagate down this lamella. Now, the advantage of this geometry is that, I'm just gonna go back to, is that the K1C, the stress intensity factor, decreases in this case as you move down, just simply due to the bending moments of the 2 cantilevers at the side. So it makes it, the geometry just makes it harder. We have to push harder to pry this apart, and that allows us, in a very simple way, much better control over propagation of the crack. And that's the trick we use here. And it's been used for a variety of different studies over the years, where we started out without the hydrogen to make our life easier, but our goal was eventually to get to these studies that I'll present today. I would like to just show, just because it was really fun for us, a study that we did on wood, using this method, just so you can see what kinds of things that can be done with these kinds of methods. Now, wood, as you know, is a material that if you try to fracture it across the grain, it's very difficult to fracture, whereas if you fracture it along the grain, it tends to fracture quite easily. And we wanted to understand this fracture along the grain, which is otherwise difficult to study because it's unstable. And in our case, because of our method, we could, in fact, watch this propagation along the grain in the wood. Now, wood is very susceptible to electron beam damage. And the image you see here is from an SEM instead of a TEM, and that's where this study was performed. The TEM was too destructive. We had to work in the SEM. I won't go into the details, but we were able to watch these cracks propagate, and you see a sketch of what we observed here. And the thing that was we found really fascinating about this is we believe that learning from the structure of wood, we think this study showed a new concept for how one can make fibrous materials tougher. And the basic idea in wood is that it's arranged the fibrils so the cracks are steered to an interface, a particular interface. At this interface, the direction of the fibril direction, it changes, and the cracks get hung up. They have to stop, they have to tear and rupture the fibrils, which requires a lot more energy before they can continue on. So basically what the material does, it's designed so that it steers cracks to a very tough interface, and the cracks get trapped there. And in order for them to move further, it requires a lot of energy. So it becomes a tough material. And of course, these concepts are ones that can be used in engineering materials, and in my opinion, would fulfill two engineering goals at one time. It allows the toughness to be controlled, and it also allows to select the failure site for the material. So just to give you an idea of what these kinds of tests can do in a very, very different type of material. But now let's go on to the case of the steel. And you can see here on the right, on the left, a microscope image of the cross-section of a specimen that's been prepared and is ready for TEM for a fracture test. So it's this lamella thickness you see here. And we've been able to do various things like identify carbides, get grain sizes and precipitate sizes in the material. And then we go in and we fracture this with the method I described. And first, let me show you what it looks like beforehand and what it looks like afterwards. So at the beginning, we have the structure you already saw. And afterwards, it looks like this. This is after it's been pried apart. And we see that we have a transgranular crack path that's running between the carbide precipitates. There's been a lot of thinning near the crack front, a lot of deformation. And important is that we have a ridge to ridge or dimpled fracture surface with extensive necking. So you can see the necking here, and things where it's where there's a valley on one side, there's a valley on the other. So this is they are mirror images of each other. And it's a very blunt tip that we produce. And now I'd like to show you a video of this. So you'll see here is in this image here on the left, you see here's the notch that's been produced and a crack that's been propagating. You can see it's quite blunt, and this is a thinned region ahead of it. And now we're going to see what that looks like in the TEM. There's a lot of things going on here. What one sees are a variety of things. I think I'm going to play it a second time. You see contrast from bending contours. That's just simply from changes in thickness, or bending from diffraction. You see voids opening up, nucleating and opening up ahead of the crack tip. So here's a void opening here right now. And there'll be one opening further up down here as well. So there's a chain of voids opening ahead. And a lot of the features you see are bending contours, but they're also dislocation motion that's going on. So that shows you what it looks like. And here you can see, in this case, this is the tip emitting dislocations. Most of the features you see here are in fact the rapid motion of dislocations, and they appear to be being emitted from the cracked tip in this case. Okay, so this is what our these types of images. Lynn made a number of these tests. What you see here is characteristic of this material. During each test, the crack propagated through many grains. So each test is involves a variety of different grain orientations and microstructures. And what we can say is that what I'm showing you here is characteristic of this behavior in the vacuum in the TEM. And so we see that the holes are nucleating ahead of the crack tip, and they join up and coalesce, and that's how the crack propagates. So here it is summarized here. You can see it thins down first by dislocation activity, and then once the region is thinned, holes open up in the lamella, and they open up between the precipitates, not next to the precipitates, and they then coalesce, and we get, as schematically shown here, a crack path that moves through the ferrite matrix. Okay, now you saw this picture before. This is the fracture surface of a specimen that's been tested in nitrogen, and you can see there are lots of carbide precipitates at the surface, which we did not see in our TEM case. So what is the difference? We're seeing here our TEM case, the fracture surface did not contain precipitates. Here there are precipitates. How do we explain this difference? And the difference in this case, it's been concluded that the reason these surfaces contain the precipitates is that the voids open up at the precipitate ferrite interfaces, and leaving the precipitates then in the fracture surface, as shown here in cross section. And the argument we make here is we say, well, in fact, the processes in the two cases are quite similar. It's just that the voids open up where the plasticity is highest. Where there's plasticity, you get voids forming. That's been usually assumed to be the case, that plasticity is what's needed in order for a void to form. And in the bulk stress state, that high plasticity region is at a precipitate matrix interface, whereas in the thin lamellas, that's in the middle of the ferrite grains. Because of the difference between the plane strain and the plane stress state, or because of the difference in the triaxiality, the result is that if we argue voids or holes will open up where the plasticity is highest, then we can explain both the bulk and the lamella case as being the same process governed by the same mechanisms. It's just that where the voids or holes are forming is determined by the stress state, which, as we said, is quite different in the two cases. So in our opinion, we can bring the TEM results and the bulk results here under one picture, and argue that what we're seeing in the TEM is revealing mechanisms that may also be controlling in the bulk case. There are some important differences due to the differences in the stress state, and they result in differences in the fracture surface. Okay, so let me now go on to the hydrogen case, which is, I think, what's of interest here. Here is once again beforehand and afterwards, and maybe you notice already that this is quite a different crack feature. First of all, we have a sharp crack that even the tip runs off the bottom of the page here. It's also transgranular and moves between carbide precipitates, and there's also extensive thinning. But what we see is that the crack tends to be a little bit flatter, and what we have here is, instead of ridge to ridge as we had before, we have here ridge to valley. So they are matching interfaces. So and this is a very, very different this is an indication of very different processes that go on during crack propagation. And so let me show you the video so that you can see how different that is. So here's our notch, and you can see we just had something happen down here, and maybe you're going to start to see somewhere in here a Here's a zigzag crack starting to open here in the material. Yep, you can see this crack now quite easily. It's still, there's a bridge still up here, but now that's going to open up and the crack is going to propagate. So what one sees here is a very, very different process. And this is something that Lynn observed not just one time, but in several specimens, and of course in different grains as the crack moves through the specimen. So what's one seeing is that the thinning occurs as before due to dislocation activity, but then ahead of this crack tip, instead of holes opening, we form these small zigzag cracks. They grow and then link up, and that leads to propagation of the crack. And so the crack remains sharp, even though there has been significant thinning to begin with. Now, if we go in and look very carefully at these surfaces, you can see here they tend to have 100 orientations, these facets. They're not crystallographically sharp, but the tendency to be lined up with the 100 surface is very prevalent. Sometimes we form new grains. That happens for both hydrogen and vacuum. I won't be talking about that much in this talk, but we see these what we call them the zigzag crack formation, and that's something we do not see in the hydrogen case. So in the vacuum case. So this is a distinct feature of the hydrogen fracture case. Okay, so summarized now in this schematic, we first thin down ahead of the crack tip, as you see here on the upper right. Sorry, let me switch back to the laser pointer. As you see here on the upper right, and then the crack propagates by formation of these zigzag cracks on 100 facets ahead of the crack tip, and then these link up and lead to a ridge to valley fracture surface, which is very distinct from the ridge to ridge fracture surface that we have in the case of the vacuum. So summarized here, the difference between the two, these dashed lines are meant to indicate the thinned regions. So we see a very distinct difference in how these cracks form and in the resultant crack surfaces. So the question we have now is, why are zigzag cracks forming? What are the possible mechanisms for that? And why is that promoted by hydrogen and not observed in the vacuum case? So one way, there is a study out there on gold without any hydrogen showing zigzag structures. It's not something that we found to be very common in the literature, these kinds of structures. In the case of this study here, they explain this by arguing that these features are formed by either shearing or twinning, and that they're activated by whichever has the maximum resolved shear stress. So that's the simple picture, is that if the applied stress activates dislocations for shearing or twinning, then that's what will happen, and the deformation will then result in these zigzag surfaces. So for our case, if we look down, we can see we have quite similar type of features. We could argue that if dislocation motion in the hydrogen is easier, which is the help mechanism, then we could imagine the following scenario. Dislocations like to glide on 110 planes in BCC iron, and if we have that happening unimpeded at a cracked tip, then these two active slip planes steer the crack path along the 100 plane in between. I won't go through the geometry of that, but that follows if one goes through the Burgers vectors that are created, so that one ends up, if both these 110 planes are active at the crack tip, one would end up with a crack path moving along the 100 plane until the applied stresses would require that to turn and move along another 100 plane. So we could argue that unimpeded dislocation activation from the crack tip on the expected 110 planes could account for these 100 facets that we see. It does require that hydrogen somehow is making this unimpeded dislocation motion very easy. And it's not, that's something that will require further discussion to come up with a watertight argument for why that's the case. The other argument one could bring here is based upon the decohesion model. And if, for instance, hydrogen lowers the surface energy of the 100 surfaces significantly, then one could imagine that as we thin the lamella down in front of the cracked tip, eventually the stresses are high enough and sufficient to cause cleavage along 100 surfaces. There are some calculations supporting the reduction of surface energies also on 100 for ferrite. However, the effects tend to be small, on the order of 10%, and the general feeling is that might not be enough to account for this effect. It does, however, depend upon the amount of absorbed hydrogen, so it's a little bit difficult to say. So it seems to me that both of these mechanisms remain possible arguments for what we're seeing in our material. I'm getting just about done. I would like to now go to the question of what we learned in the lamella case for hydrogen is that can we use that to explain the quasi-cleavage fracture surfaces that are observed in bulk specimens? And we believe that that's the case because our surfaces tend to be somewhat straighter and somewhat flatter. We would argue, it's a fairly phenomenological argument, but we would argue that if the cracked tip remains sharp, then the crack will tend to propagate where the applied stress sends it, and it's less sensitive to the microstructure, and so it will tend to be flatter to begin with. So as soon as one has a sharp tip, we think that at the macro scale, one would expect flatter surfaces, fracture surfaces, and these 100 facets that we find at the submicron scale are, we believe, consistent with the type of observations one sees, for instance, here and on surfaces like this here, where these facets, we don't know the orientations of these facets, but we believe that these facets we see in the TEM could have the same mechanisms that are causing these faceted surfaces here, or apparently faceted surfaces here at the fracture surface for the hydrogen case. So we believe that what we're observing in the TEM gives us some clues about how we get these quasi-cleavage surfaces in the bulk case. Both of the mechanisms I propose could be active in the bulk case as well. So we're unable at this point to tell you which mechanism we think is dominant here. Maybe both of them are active. That can entirely be the case. This is a rather long list of the summary of what I've basically just said. And the point I want to bring up is that both of these specimens, before the crack propagates, there's significant thinning. And so far, we have not seen a difference in the effect of hydrogen in that initial plasticity ahead of the cracked tip. That's something we're going to look at very carefully, because that's basically the evidence for a help mechanism, would argue that the plasticity should be different in the two cases. So far, we have not seen evidence for that. So that's something we need to look at more carefully. But once it's thinned and the stresses are high, ahead of the cracked tip, we see very, very distinct behavior between the hydrogen case and the non-hydrogen case. In that one case, we get holes opening and dimples forming, and in the other case, we get these zigzag cracks, which we think can account for the quasi-cleavage surfaces one finds in bulk materials. So I know I sort of rushed through these things at the end, but we've basically, as is often the case with research, we've seen a lot. We've got a lot of observations, but we have more questions for more studies we need to make in order to really tackle which mechanisms are dominant here. But we think these kinds of methods offer an important way to understand what's going on in these materials, and that it's possible to extrapolate from the stress states of the TEM lamella to the bulk geometry if one takes care. And so with that, I'd like to thank you for your attention, and I'd be very happy for any questions.
Professor Volkert, thank you very much for your exciting presentation. Yeah, it's very interesting. Actually, I have many questions. But so now let's open discussion. if you have questions or comments, please let me know by raising your hand, or you can speak directly. Please.
Can I ask a question?
Please, Professor Makadore.
Yes, thank you very much, Professor Volkert. Yeah, I have many questions like Professor Kubota. The main one is actually, I think, the one you mentioned at the beginning, which is I think the one question one everybody has when you have an atmospheric cell with the TEM is what would be the equivalent between like you said, you have very low pressure, but it's activated by the electron beam. And so it would be very nice in some time in the future to know the equivalent fugacity or pressure. But like you said, it's very difficult questions. And related to that, actually, I've been also, as you know, because we've been working on this, working on looking at the data from pure ion with hydrogen before. And one of the last calculations I've seen was by a group with Dr. Yu in 2020, and they reported by calculations that they didn't see any evidence in the calculations result for the help mechanism, and they reported only that the dislocation core would change with hydrogen, the core structure, they specifically the core radius. And this has been also hinted at by Professor Barnouche with the nano indentation, and he said maybe the shear modulus decreases with hydrogen, and maybe the core radius increases. And there have been a few papers so far, mainly calculations. And the main issue with calculations, as you know, is that it's again, like with the issue of the thin lamellae compared to the bulk, is that it's a few dislocations and a few atoms, so it's very difficult to get the effect of the group of dislocations. But a lot of data seems to hint that the shear modulus will decrease with hydrogen, but not so many data, confirm the effect of on the stress field of dislocations. And so I'm wondering what are your views on these? And yes, basically it's going from the effect of, some people have also said that because the electron beam activates the hydrogen a lot, what we see in TEM would be something that cannot be seen in usual hydrogen exposure conditions, because it's too high a fugacity, and so it's a true thing that's happening, but it's not reflecting the reality in the, how do you say, room temperature and usual hydrogen gas pressures. So I'm sorry, I'm rambling a bit. I want to know your thoughts on those random questions. Sorry.
Okay, well, thank you. Those are really good points you brought up. So I'll just say a few words about the fugacity and a few words. I don't think I'm going to be able to answer your questions in detail, but I think we'll have opportunity to discuss this further. But just briefly, your point about the fugacity is possible that it's raised to, say, unphysical values by the electron beam. That's something we simply don't know. And I don't know of a way, because it depends upon all kinds of things, like where you're looking on the specimen relevant to the edge of the holder. It depends upon details of the geometry in the chamber that will be different for every experiment. I think coming up with some specific prediction for what the fugacity of the hydrogen is in the TEM will be very, very difficult. I think there are some general trends we need to clarify. What is the electron impact dissociation for absorbed hydrogen that's already on the surface, for instance, or ionization? What are those cross sections? What are the relevant, is it electrochemical? What's driving the material, the ingress of the material? That's something that I think general information would help. But then I think we need to find a way, some way to measure the hydrogen concentration by some material, for instance, where there's a known lattice constant change with hydrogen, for instance. Those are the kinds of things that I think are going to be the way to get at that for the TEM. We'll be actually finding material where we can measure the change in lattice constant with hydrogen and using that to measure what the hydrogen concentration is. I think that's probably that method there. In the meantime, yeah, I suppose it's possible we do have fugicities that are unphysical. We haven't seen hydride formation in this case. I didn't talk about our studies on titanium, where hydrides can be formed and where we did not see hydrides form. So although we saw effects of hydrogen on the crack propagation, so that would suggest the fugacity was below that needed to form the hydrides. So, but okay. To the help mechanism, I'm using the term help to include both the shielding as well as changes in the core structure leading to, for instance, easier formation of kinks or other changes in the core structure. I know that that's maybe not the standard way to do it, but both of them, I believe, are going to lead to hydrogen-enhanced localized plasticity. So I include both of those in there. As far as the shear modulus, I need to look at those. I'm afraid I'm not all that well informed about where that is. You can have a change in shear modulus because you've changed the bonding, which of course requires a very high concentration, or one has inelastic contributions or anelastic contributions. Maybe that's, but maybe we discuss that here further, or maybe we save that for another point. And in the meantime, I will look into that literature more carefully.
Thank you very much. It's you make a good point about the lattice constant. Actually, I've seen it in stainless by XRD. We can see it, the increase of lattice constant with the increase of hydrogen exposure pressure. So maybe there is something to do like bulk and then compare with what you get see in situ with the TEM. Yeah, but the point about the shear modulus is that it seems I've been reading a book made mostly by chemists about hydrogen embrittlement, and it seemed to them that it was kind of obvious that the bond would change from a more metallic aspect. It will switch between metallic and covalent bond, switching from one to the other. But I don't think it's been so much talked about in the more material mechanical engineering community. So it's something I think we should look at. But like I said, many of them are calculations. And for instance, one of the most, I would say not famous, but the one that's been most repeated was by Professor Gavryliuk from Ukraine. And the issue I have with those results is that they calculate the values for FCC iron at room temperature, which cannot be checked experimentally. So anyway, it's just, it's something that's hinted at in the literature, but has not been completely confirmed yet. And I think it's maybe, anyway, an interesting point, but we should look into it. Sorry for the rambling again. Thank you again very much for the presentation. Thank you very much.
Thank you for the questions.
Thank you, Arno. So 2 millibar hydrogen is enough to change the fracture mode. So if the hydrogen pressure is 1 millibar or 0.5 millibar, so what happens? Can you expect?
So of course, if without the electron beam, 1 millibar of hydrogen and room temperature in ferrite, I do not believe will lead to significant dissolved hydrogen to change the crack propagation behavior. I think that that's something that I have learned from talking with you and colleagues, that is, we would not expect that to change the crack behavior. And that's why we conclude that the electron beam and the conditions in the microscope are significantly enhancing the fugacity of the hydrogen. We are not the only ones to see that. There are many studies on different materials in different countries, different microscopes that show that very low pressures of hydrogen, below what would be expected outside of the TEM to produce an effect, can produce a large effect in the TEM. So that the fugacity is raised, I think, is clear from the observations. How it's raised remains a mystery.
Okay. So we have a question from the audience, from Aman Arora. Not a question, but just a comment. Very fascinating work. Thank you, Prof. Cynthia and Prof. Göttingen for this informative presentation. And Dawei Lee, thank you very much for the impressive talk. I am a postdoc at Kyushu University. I'd like to know how you fabricate the very thin specimen. Did you use FIB or other techniques?
Yeah. So yes, these specimens were prepared by focused ion beam. I was seeing if I could move back in the yeah. Okay. Oops. I'm not quite sure. I was trying to move back to the image of the specimens. They were prepared with the focused ion beam. And there are, of course, there is, of course, damage at the surfaces. So this is this geometry you see here. This is all cut with the focused ion beam. That's correct.
Thank you very much. Okay. And another question. Does anybody has any questions? So Petros observed beneath of the fracture surface created in the presence of hydrogen by the pick-up TEM technique.
But I'm sorry, I didn't understand.
Site-specific TEM, combination of FIB plus TEM.
Right.
Petros observed very significant evolution of dislocations beneath of the surface in the presence of hydrogen. So do you have any common feature with their observation in your experiment?
Yeah, so I'm familiar with those studies showing that, if I recall correctly, that some of the features on the quasi-cleavage's surfaces, such as we show here, can be associated with significant dislocation activity. So we see significant dislocation activity in our specimens before the zigzag cracks open. The fact that, and I'm now going to go to another view graph. Here, the fact that these features here are not purely crystallographic, and yet the tendency towards roughly 100 is very strong. One way to explain that would be to say these are in fact cleavage planes that have subsequently undergone dislocation motion, leading to roughness. I believe that's that the argument that I tried to show a little bit later. Here, that we would get roughness at these 100 facets due to dislocations that showed up after the zigzag crack moved through. Once the zigzag cracks are formed and link up, associated with the zigzag crack formation is not as much plasticity as for the case of the holes. I mean, I think that that's fairly geometrically fairly straightforward that would be the case, but there is plasticity continuing. So there's nothing we've observed that disagrees with those observations. A direct connection is the kind of thing we're hoping to get more information from. We're really hoping to find a way to get more information about the nature of the dislocation motion and arrangements ahead of the crack tip. That's very difficult, but that's our hope, is to get some more information and to look for differences between the vacuum and the hydrogen case.
Okay, thank you. Thank you very much. So, are there any questions from audience? これは石原先生あるの
Yes, I have another one.
Okay.
If you don't mind. About the FIB, just to follow up on the previous question, did you have, maybe you mentioned it, I didn't hear, did you have issues of FIB setting that would change the structure of your material, like amorphous surface effect or recovery of previous deformations, things like that?
I don't think we have a lot of evidence of that, but over the years we've used the FIB very routinely for preparing specimens. That's something that, among other things, Lynn is a real expert in. And I believe that the methods she uses are ones that are already optimized to be as nice to the material as possible. Nonetheless, there is always damage at the surface that is produced by the FIB. There's no question,
Okay.
and there are impurities as well. And that's actually not something I listed under the TEM challenges, because those are not necessarily something that come with the TEM. But yes, FIB specimens are different, and particularly for in situ tests, where one's not just looking at what does the structure look like, but rather how are the dynamics of the material.
Yes.
And if they're changed by the presence of gallium, for instance, or by defects that you've introduced with the FIB, then yes, that's a very important point. So thank you. I should have made that point.
No.
I did not, but yes, the material is different as a result of the FIB surfaces. But it's as small as we can make it, basically.
I have to say, I trust your own methodology, because I've seen you guys, how do you work? But I've seen, remember, maybe a year ago, a couple of years ago, Dr. Harris, Zachary Harris, he presented at the yearly heterogeneous seminar, and he had shown actually a FIB manufactured sample with various power levels, and one after testing in tensile test, and I think, and actually one of them looked like a deformed material, and one looked like how to say annealed material. And so I've been always since then very careful about my own and others to see how they prepare. It's one thing I wanted to check.
That's one should remain careful, and we have to too, and we always have this question in the back of our heads.
Thank you very much for the answer.
So the time is almost running out, but we can accept several questions. Is there any questions? Today, do you talk about the crack propagation and the monotonic loading? You show the crack nucleation in front of the crack tip, separated from crack tip. But I am very curious about the fatigue. In the case of fatigue, probably crack is always start from the notch root. Probably different things can be observed.
Yeah, that would be an interesting thing to test, and to see whether one gets the same. It would be an important test of the method to see if we got similar differences in the TEM to what's observed in bulk cases. I believe those experiments would add a level of difficulty that I think we'd like to put our efforts in the next time on doing the high temperature work for the kids.
Okay, all right. Thank you very much.
But maybe after that.
Okay. Good. All right. So, do you have any questions? This is the last call. Is everything clear? Okay. If no more questions, shall we close this webinar? right?
Okay.
So, Professor Volkert, thank you very much for your very interesting talk. So let's thank the speaker again. Thank you very much. So,
Yeah, thank you. My pleasure.
also, I thank all of participants for your cooperation. So, see you at the next meeting. So, thank you very much.
Thank you.
Bye bye.
Bye.
Thank you very much. See you tomorrow. Ishihara sensei, thank you
Okay.
very much.
Thank you very much for your nice talk.